So, good day students, and welcome to the first nugget in the lesson dealing with biofuels and the conversion of biomass to biofuel. When you talk to people outside the energy sector, it's often understood that biofuel would be a car fuel from biological origin. But from the previous lesson and the terminology introduced in that lesson, you know that a biofuel is a tradable and combustible substance. And you may remember from figure 3 in the Unibet report from FAO that there are lots of different routes to go from biomass to biofuel and then go on to bioenergy. Except from biofuel, there is another word that is often subject to misunderstanding, and that is the word upgrading. Upgrading is often used as a synonym to conversion. But if we define upgrading as a process in which the quality is improved, we run into problems, because then we end up in trying to understand what fuel quality is. So in this nugget we will discuss fuel quality, and especially we will talk about the heating value and the energy density. When you looked in the UBET report in the previous lesson, you will have noticed that there is no specific definition of fuel quality. And that is because there is no such thing as a unique measure of fuel quality. Page 6 in the UBET report will introduce the problem to you. In the last paragraph on that page, you will read that a major motivation for quality assurance is to fulfill legal limit requirements or to meet technical demands for the power plant. To guarantee these basic conditions, chemical and/or physical parameters may be varied theoretically by crop production processes as well as by harvesting and preparation. Now, to summarize this, we may say that fuel quality is a measure of how well the fuel is adapted to the end-user process demands. A cheap biodiesel containing paraffins may be a high-quality car fuel in a tropical climate, but not in the Arctic or subarctic region. And that would be because the paraffins will condense and clog the engine at low temperature. Wood pellets is a high-quality fuel if you want to heat your house using a boiler, but not if you want to run an aeroplane. The thing is that biofuels are so very diverse. Look back at figure 3 and figure 5 in the UBET to refresh your memory. And then, if you go on to section 3.2, page 11, you will read that the aim of biofuel processing is to provide fuels with a clearly defined fuel characteristic and ensure a technically simple and environmentally sound conversion into useful energy. So what we will do now in this nugget is to concentrate on one important fuel characteristic, namely the concentration of chemically bound energy. But first of all, let me remind you that the BusyPlan handbook appendices deal with fuel descriptions and different aspects of fuel behavior. So, now for the heating value. There are different standards to determine the heating value depending on if the fuel is gaseous, liquid or solid. But there are common and basic things. First, all standards basically use a bomb calorimeter. In this apparatus is a specific amount of fuel inserted. Then enough oxygen is added to guarantee that all the fuel can be completely burnt. The calorimeter is an enclosed volume that can be maintained at about a constant temperature, typically 25 degrees Celsius. The fuel is then ignited and the combustion products are cooled to the starting temperature again. And then is the amount of energy extracted from the combustion products recorded. The procedure becomes slightly different depending on the state of the fuel, but basically this is how it is done. Let us now look at this a little bit in more detail. The picture in this slide is copied from the appendix about fuel analysis. The gross energy released from the fuel is all contained in the part of the fuel designated combustible. And this is the dry and ash-free substance. Ash and water cannot be combusted. But while ash is per definition regarded as inert in this context, is water definitely not inert. Because what happens is that the liquid water in the fuel boils off to form steam, and that will take energy. In the calorimeter is the process started at 25 degrees Celsius, and it also ends at 25 degrees Celsius. When ignited, will the combustibles in the fuel form hot gases, and then does the water vaporize. This requires energy. The energy need is proportional to the water content in the fuel. The hydrogen in the fuel becomes water vapor during the combustion. So the mass balance for water shows that the total amount of water vapor is bigger than the moisture content in the original fuel. So we count this water vapor together with the vapor from the fuel moisture. But then is the whole thing cooled again. So what we have after that is cold gases and condensed water. But the amount of water is now bigger than the amount of water we had from start. So the heat released from the condensation is bigger than the heat required for the vaporization. So let us now look at the heat balance. As you will see from this slide, will the experimental value give as a result a total energy release from the calorimeter that is higher than the energy contained in the combustible substance. Expressed per mass unit, joules per kilo wet fuel, is this value called the calorimetric or higher heating value. This is the amount of energy that could be extracted at the most in case all the water vapor in the combustion gases was condensed and all the condensation heat made use of. But in most real cases will the combustion gases leave the plant in the form of gas, so the cooling is much less. And in that case, will there be no release of condensation heat? Expressed per mass unit, joules per kilo wet fuel, is this value called the effective or the lower heating value. This is the amount of energy that can be extracted at the most in case the combustion products all leave the plant in gaseous form, and this is the normal case. So this is how the experiments in bomb calorimeters can be evaluated. Different countries tend to have different traditions with respect to these two heating values. Some countries use the higher heating values, others tend to use the lower heating value. In Scandinavia, we always use the lower heating value. So if I say the heating value without any specification, I always mean the lower effective heating value. And let us now look closer to the equations we have found. What I've done here is to replace the numerator in the two equations from the previous slide with the more detailed expressions. The desired value is the heating value for the dry and ash-free substance, delta H sub DAF. This value is readily available from the measurement. In the equation to evaluate delta H sub DAF are two values that have to be taken from a fuel analysis. The fuel sample input to the calorimeter will be wet and contain ash. So, to determine M sub DAF, must the moisture content and the ash content be known. And to compute the amount of water formed from combustion of the hydrogen in the fuel, must the hydrogen content in the dry ash-free substance be known. Following the fuel analysis terminology as described in the busy plan appendix, it is clear that the mass of the dry and ash-free substance is the fuel mass minus the amount of water and minus the amount of ash. Expressing this in terms of fractions, moisture mass fraction F sub W on a wet basis and the ash fraction F sub ash on a dry basis, just as usual, we find the dry and ash-free mass M sub dAf according to this slide. Here, M sub F is the total mass of the wet fuel with the ash in it. The amount of water, M sub 1, from combustion of the hydrogen in the combustible substance is computed from the hydrogen content, F sub H dAf, in the dry and ash-free substance. And the amount of liquid water in the fuel sample, M sub 0, is determined from the moisture content, F sub W. Knowing delta H sub dAf, the ash and water contents and the hydrogen content in the dry and ash-free substance, can both heating values readily be computed. And these equations are general and valid for all types of fuel, solid, liquid or gaseous. It is important to notice that the heating value is always expressed as energy per mass unit. In some cases, it is more relevant to use a volume measure, and the volume-related measure is called the energy density. To obtain a value for the energy density, we have to know the bulk density. The energy density is most relevant when it comes to judging and comparing modes of transport. In transports, it may happen that there is a specific volume, like a container, that can be filled to the rim, and this volume is the limiting factor. So there is a specific maximum number of cubic meters that can be transported at one go. In such cases, will the total amount of energy represented by the fuel in the container be proportional to the number of kilos that can be fitted into the container? If the number of kilos can be doubled, then the total amount of energy is also doubled. The bulk density is the weight of the material once the container is filled to the rim, divided by the container volume. So the way to obtain the energy density is simply to multiply the heating value with the bulk density. In the homework session, we will take a slightly different approach to the heating value, so see to that you are perfectly comfortable with what we have said so far before going on to the homework.